Okay, I'd like to tell you about springs in series and parallel. Let's start out with series. Series just means that they're one right after the other. And we want to be able to develop what the effective spring constant will be of the combination of these two springs. So we can treat these as though they're one spring with a particular K called the effective spring constant. Okay, so what we're going to do is we're going to put a force here of F. And when you put a force here, that force is throughout each spring. So the force is the same here, as here, as here. It's all the way up and down the spring. That's tension, right? So the tension is the same throughout. Okay, so what will happen then is this will stretch and that will stretch, but the total stretch we'll call X total. And the total stretch will be X1 plus X2. Okay, now if we use Hooke's law, F equals Kx, we'll ignore the negative for a little bit here. Then X is equal to F over K. And so what I'm going to say is that the X1, how much will it stretch? F over K1. And how much will X2 stretch? F over K2. And so if we wanted to replace that with one spring that had the same spring constant as this combo, that would be F and that would be K effective. Okay, well, the F's can cancel out. And so we're left with is 1 over K effective is equal to 1 over K1 plus 1 over K2. If there were more, you'd just have plus 1 over K3 and so on. So they add like resistors that are in parallel. So they're kind of the opposite of resistors. When resistors were in series, they added, but when they were in parallel, they had the 1 over R equals 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Sometimes this is called K equivalent too. All right, let's take a look at springs in parallel. Okay, now these springs are in parallel. See how they're parallel to one another? And I'm going to put a force on here. Okay, well, when I put that force F on there, this is going to divvy up that force. And so like this will pull back and this will pull back with F1 and F2, let's say. So the forces, the force that I will have to pull, if I'm pulling these springs, I'm going to have to match this force and this force. Think of this as one person and another person. If they're both pulling with 4 newtons, then I'm going to have to pull with 8. And so if this person's pulling with 4 and that person's pulling with 4, I'd have to pull with 8. So F total is equal to F1 plus F2. And if there were more, you'd say plus 3 plus 4. I'll just do 2 for right now. Okay, well, but that's equal to Kx. So K effective times X is equal to K1 times X1 plus K2 times X2 plus, and we'll put more on if we need to. Okay, well, if this bar stays straight, then we're going to assume that when you pull, you stretch this the same as this. We're just going to assume that. And so you have to get this equation. And so when you do that, the x's are all the same, so they can cancel out. So K effective is equal to K1 plus K2 plus and so on. This is for series. This is springs in series. So they just add up. They're kind of like resistors in excuse me. I misspoke. This is for springs in parallel, and it's the same as resistors in series. Okay. All right. So let's see how this applies to some problems. we have a mass on a spring. Here's a mass on a spring. And then we take two other springs that are identical to this one. We put them end to end. And we pull this down. How will the period of this bouncing up and down, how will it compare to the period of this bouncing up and down? Okay, so let's see. The period of this is going to be, the one on the left is going to be equal to 2 pi times the square root of m over k. That's this one. Now this one is going to be 2 pi times the square root of m. Now, what should I put for k? Well, k, since these are in series, I have to do the 1 over k effective is equal to 1 over k plus 1 over k. And so that's 2 over k. So k effective is k over 2. If you flip both sides, if you take the reciprocal of both sides, the effective spring constant, it's actually less than just 1. And it makes sense because it's a much easier spring to stretch. It's not so tough. The bigger k is, the tougher the spring. And this, you put the same force on this, and this stretches twice as much. I think you could see why it would stretch twice as much. You have twice as many coils. Okay, so for this, I'm going to put k over 2. But when I do that, that 2 comes up here. And so this will be, the one on the right will be equal to the square root of 2 times the one on the left. Square root of 2 is about 1.4 times, so it's going to take longer to go up and down, about 1.4 times longer to go up and down one time. Okay, lastly, what happens if we, to a spring's constant, if you cut it in half? Okay, well, if you cut it in half, then when you put the same force on it, let's look at spring constant is equal to F over X. So if you cut a spring in half, you take one of the halves, you put the same force on it, you only have half the coils. And so because only half the coils are there, when you put the same force, you'll only get half the stretch. So when you cut a spring in half, this is the original. Then we cut it in half, and the same force will only give you half the stretch. And so that 2 can come up top. So the k goes up. This is the new k. So the new k, we'll call that k prime. K prime is going to be twice the old one. All right, that's all I have for you on this one. See you in the next one.